Okay, good evening, everyone. So thanks for coming. And then today is our finale, right? So our final SBAR during this pandemic, and thanks for coming. And so today we'll have Renna, which was in the same office with me. And then so hopefully we can meet again soon in person, right, next semester. So Renna is a second year PhD student in biophysics. She's now working with Professor Paul Volkowski, and then so she has lived in 3 countries, and then enjoys books, board games, and video games. Yep, hopefully we can play together. Okay, so yeah, Rena, please take it away.
Okay, so I'm going to talk about the origin of life, which has historically been a very interdisciplinary problem. So it's generally agreed that life emerged around 4 billion years ago, and a question that has never been answered is how then I'm going to tell you about how people try to answer this question from chemistry and from physics. So the first thing we need to answer the question would be a definition, and unfortunately, people don't agree on the general definition. So but people agree on some general requirements, which are that living systems have to self-reproduce. They're based on chemical reactions, and they undergo Darwinian evolution. Also, when we talk about the origin of life, we expect something that's very different from modern because modern life is based on highly complex molecules, such as DNA, RNA, and proteins, which are only produced if we already have living things. So we want a living thing that's synthesized from very simple chemical compounds that can be produced abiotically, and for the 1950s, some people called Miller and Urey demonstrated that you can get amino acids just by putting electricity through oxygen and hydrogen gas. So we can distribute the short peptides, which are much smaller proteins, but so far no one has shown you can get RNA so the goal has been to make a living system out of short peptides, and it's actually been successful because there are small experimental examples. And the way they know that they've made a self-replicating reaction in the lab is they observe exponential growth in one of the chemicals. And so this is an experimental example. Where they made sequences of amino acids. They measure the concentration over time, and they observe that the concentration of this peptide 1 increase exponentially over time. And the proposed mechanism for how it happens is shown here in scheme 1. And it's actually quite amazing that they were able to get this to work, because they don't actually know if that's the correct mechanism. And this brings us to the question of, are they alive, given that we have a self-replicating system that's made out of amino acids, and the general opinion is no. And the problem are that all of these experimental examples so far are much smaller than modern living networks, and there's no easy way to make them bigger. Also, modern biochemical networks operate through electron transfer reactions, and none of these have that. And we want to assume that the origin of life happened only once, and everything that came after was a product of evolution. And so for the remainder of the talk, I'm gonna talk about evolution. So another approach to the origin of life is just a general mathematical framework for self-replication. So we define the self-replicative reaction to be a reaction where the product is also a reaction. And these may follow a simple reaction scheme, or they can be a complicated system of reactions. Where no single reaction is self-reproducing, while the system reproduces as a whole. So so a general mathematical framework for this kind of thing started with a guy named Tsung-Chi, and later we got a more formal framework that goes like this. You divide your molecules into 4 sets or 3 sets. The first set, the catalyst set, and the product set, which are connected by a set of reactions. Every molecule in the system can be made from the first set. Every reaction is catalyzed by something in the catalyst set, and every catalyst is also a product. And here's an example. where the molecules are represented as strings of bits. So, if you define it this way, it turns out that these sets have a certain network structure, and that can be deconstructed into minimal reproducing units. And as it turns out, all self-reproducing networks can be reduced to these minimal networks. And over a few decades, some people worked out, many different formalisms, like not just one answer. Any framework for self-reproducing reactions can be reduced to minimal reproducing units. And this is where we can start talking about evolvability. So, as we said, we have to have a system that is capable of evolving into the modern system. And by evolving, we mean survival of the fittest. So the fit individual will survive and continue to reproduce, while the less fit are gonna die. And to do that, we can see something like that if we put together multiple self-reproducing core units that compete over the same food molecule. And this has been demonstrated computational so here is the example system I had earlier, and we have 3 computer reaction systems that use the same food molecules, but little reaction and products and they simulated these systems over a series of time steps where they give each reaction some probability of happening at every time step. And once you get to the product of one of the systems, the reactions in the system become more likely because they tend to increase the rate of their own formation. And these are said to undergo competition because this differential survival of the force. And after this, this actually raises another question, which is this is a type of evolution good enough to generate more complex structures like we see in modern networks the general opinion to that question is no. Um, so when people say, well, we need to have a system that's capable of what is called continuous generation of novelty in response to environmental stresses. And that, unfortunately, is not very clear, which led people to say, that we should define life differently. And particularly, we should define life as the emergence of top-down information processing. So usually when we model a physical system, we have the dynamical laws of the system and states of this which are dependent of each other, and these people say, well, in living systems, these dynamical laws can update every time you change the state of the system, which occurs because of information processing. And if we're able to explain the emergence of a system like that, we'll be able to explain evolvability and unfortunately I was not able to find a quantitative example how to do that. Okay. So that's all I have. Is my summary. Is if we want to demonstrate the origin of life, we would have to make something from scratch in the laboratory. When we haven't done that because and we have small examples that are really living. Yeah. Okay.
Thank you so much, Renna. Maybe first let's unmute ourselves and first give Renna a big hand. Excellent job.
Yeah.
So I think we can start to. What's that?
How much of that did you understand?
I understood most of it. I think the words that you had on the slides, you kind of like followed them and then went off on explanations step by step. So I pretty much got most things, but a lot of it went over my head because I'm not a biophysics person. But it was really cool.
Okay. Thank you.
Yeah, anyone can ask any question. I think we can open any question now, please. Yeah.
Regarding the REF sets, can you go back to like the diagram and describe like which piece is the food set or the catalyst set? Because I couldn't really tell, to be quite honest. So I think the example, yeah, that one where it says like framework works too. But yeah.
So the first set is 0 and 1. The catalysts are these open boxes. The products are the black dots. So
Okay, I'm just thinking because like the only time I've only seen like figures like this in graph theory, so I don't know if you know a bit about that and how that could be used here, but it's just something that popped up while I was looking at this. But yeah, it's kind of like getting information. It's kind of getting information from just the way that this diagram is drawn, which you can, it's true to some extent, but I don't know how much formal results you can use in that.
Yeah.
You know.
So they use graph theory to reduce it to these minimal steps. I was done using graph theory,
Okay.
not by me, but by other people.
I think it's also very interesting, like in slide 14, right? You can see that there are two scenarios you can have. One is like coexist, or one is like outcompete, right? Yeah, those two. Just from this like this model, and you can kind of see, well, there can be two possible outcomes, if that's something I understand correctly. Yeah.
I mean, these are randomly generated, so it depends on who gets the food. First.
So like these in this, I don't know, like the first thing that I thought about when looking at this is like, I know it's supposed to like, I was thinking like, are there any decay mechanisms just based on the protein structure in itself? But I don't think this like formalism is accounting for that, right?
No.
Yeah. Okay. I'm just overthinking, I guess. But yeah, no, that is cool.
I actually had a question about this slide. So there's the two possible attractors, and the system ends up in two different states, but they start with the same initial conditions. And I see that the paper references something about evolvability. So it just ends up in those two different systems. I don't know what I'm asking here. Is there anything else that causes it to evolve? Like, is there anything in as the simulation is running, or does it just start with the initial conditions? And
With the initial conditions, and at every time step, each reaction has some probability of happening.
okay, that makes sense, I think. Yeah, like I said, a lot of this goes over my head, but it's really interesting.
No, I see. So like you're saying that, for example, if you're gonna go from say like, 0, 1 to 0, 1, 0, you had an associated probability assigned to that process. Is that what you're saying?
What was that?
So like for each, wait, what?
Was that? Okay, so one thing I forgot to mention is these This gray line, the dotted line, means this molecule catalyzes this reaction. So if you have more of this product, this reaction becomes more likely to happen. And that's why if a certain product comes into existence, it's gonna stay in existence because it catalyzes its own formation. So if the product is there, it's gonna make more of itself at the expense of the other species.
Can I ask a question?
Um,
So these are all like theoretical frameworks, right?
yeah.
Okay. So like how hard is it to do like a real experiment? What do you think?
Um, well, this was a real experiment,
Oh.
but they have very few examples of real experiments because it's one thing to like to simply define a system, but if you want a real system, you're subject to chemistry So whether or not a reaction happens would depend on the molecular structure, and this does not account for that. So it's actually been very difficult to construct more complicated systems.
Thanks. Any other question? Maybe I can ask one more. So like, is this like your current project, or can you talk about like your current project or something like that? Your research a little bit, and then yeah, just let us know a little bit.
Okay.
Because we are not bio, maybe here we all five are not biophysics, right? So maybe you can talk about a bit your research.
So none of this is my own work. I'm actually not sure what I'm gonna do, which is why I have to spend probably next summer trying to figure out what I'm gonna do.
Yeah, right after the call is always confusing, I've heard, for everyone to kind of try to figure out what they want to do next. What's going to turn into a good project.
This is my group. I don't know what they wanted me for.
Any other questions, comments? Three, two, one. Okay, then thanks all for first. Thanks Renna for accepting this invitation, right? And then it's an excellent talk, and thanks you all for coming to our finale, right? So I think today's Renna's talk is a fantastic talk that is super suitable for our finale, right? It's like pandemic time, and then you still show up, and then you still giving the talk, and then you're all very brave, and then so I really hope to see you in person soon, and then good luck to your life and research. And yeah, that's it. Thank you so much. Have a good day. Bye bye.
Thank you for the talk. See you all soon.
Thank you very much. Have a good summer if I don't see you guys.